Good morning. My name is Ann McCormick. I'm a technical leader at Cisco. I work on Metacloud deployments. Well, let me start with what Metacloud is. We're an on-prem managed private cloud solution. Managed meaning that Metacloud goes in with their awesome ops team, installs their deployments, and then continues to maintain them going forward for things like upgrades. And what I do in particular at Metacloud is to bring in Cisco technology into the OpenStack deployments, basically bringing in the power of Cisco networking into OpenStack. So, I should probably also mention what the heck I'm talking about. So, fast data and packet processing, virtual but for reals. So, how do we achieve fast data and packet processing on a virtualized platform? For that, I give you vector packet processing, VPP. And for a quick overview, what is VPP? It's basically open source, optimized packet processing. It can provide virtualized switching and routing for the layer 3. It supports cloud, NFV, and SDN deployments. It can run on commodity CPUs, and this is really important because basically that means customers for their hardware, assuming that the hardware supports DPDK, VPP can run on it and optimize things. VPP was initially developed by Cisco, donated to the FIDO Foundation, the Linux Foundation Fast Data I/O project. FIDO includes other projects as well, and my understanding is that some, if not all of them, have something to do with DPDK, the Data Plane Development Kit. And Cisco is still an active contributor to VPP. So what does VPP do? If you look at my handy-dandy diagram here on the right, you can see that as packets come into the NIC, the DPDK, that is such a mouthful, I'm sorry, I'm trying. DPDK processes the packets, throws it into huge pages in the Linux kernel memory. Then the VPP stack comes along and takes the packets out of the huge pages. But what's important here is that it doesn't take them out individually. It takes them out as a vector of packets, meaning basically a whole chunk of them to be processed simultaneously. And what that does is it reduces context switching and it increases cache efficiency. So this is where the optimizations come in. And I wanted to mention that VPP is modular. So as new protocol support is being added, it's very easy to put it in. And there's two existing stacks today. One is networking VPP for the OpenStack integration, OpenStack, which we all know and love. OP-NFV, which is open platforms for NFV, basically open daylight. Those are the two existing stacks. What's the status of VPP? Networking VPP, which as I mentioned is the OpenStack integration, is currently on release 1704, which gave us L3 support, VXLAN GPE, role-based access control, and graceful restart. The next release, which is coming down the pike, brings us security improvements, things like remote group ID support. It also brings us better L3 HA, multiple routers, and VRRP, virtual routing redundancy protocol. VPP will be included in popular distributions in the future, and I was told to be vague here, so there you go. And partners are, as we speak, adding support for new stacks. I'd love to tell you all about this, but I'd have to kill you. So let me move on to what I can tell you, which is VPP is available now on Metacloud deployments. So let's talk about VPP on Metacloud. What does it buy us? It allows Metacloud to take advantage of L3 fast packet processing. In the case of Metacloud, we use the N9K and the ASR router as hardware platforms to really speed things up. But we use VPP for the packet processing. And the use cases for VPP on Metacloud are for NFV deployments, high-performance VPN, and media workloads. If you think about it, the time when you really need optimized packet processing is when you've got a steady stream of things or a lot of things coming in. In the case of media, you can think of like streaming Netflix or something like that. Video and audio are particularly sensitive to delays and to jitter. So it's important to get the data in, get it buffered. And for NFV, your big data kind of deployments, it's very important to get things moving quickly. Okay, so let's take a look at what this looks like. In green, you can see a controller node, which is where we run our services. And on the left, we've got our OVS stack that we know and love. And what talks to that is the Neutron server and the etcd process. I just want to mention etcd is used by VPP in order to journal ports that are coming up. So basically things that are in flight. Before the work is done, it gets journaled in etcd. So it's kind of critical. Then on the right on the controller, you can see, I think I showed this before, but you've got the NICs, you've got DPDK, you've got the VPP stack, and on top of that, in the case of the controller, it's the DHCP agent. So any DNS requests and DHCP requests are going to be optimized by VPP. Now let's take a look at the compute host in blue. Again, we've got the OVS stack, and that's for Nova Compute and for the VPP agent in order to bring things up on the control plane. Then we've got our optimized stack for the VM traffic. So basically the hungry VMs that are just waiting for all that data are going to be using VPP. Oh, and I should mention we've got 3 VLANs, a tenant VLAN, that's our data plane, a service VLAN, and an admin VLAN. Those 2 are control plane traffic. So let's blow this up a little bit. And now we've got 3 controllers and 3 compute hosts. As I mentioned, the VLANs are terminated on the N9K switch, which goes out to the ASR router, out to the real world. I wanted to mention on this slide in particular, etcd again, because we run in a 3-node cluster for etcd. Etcd is used like a database for VPP, so it's important that it has redundancy. And by running in a cluster, it uses the Raft protocol to provide resiliency and redundancy. So what did it take to get to production quality on Metacloud? More than fits on a slide, but these are the highlights. The first thing was to get to Liberty. Metacloud is currently running on Liberty, so we had to backport. Another thing, when we were first starting out, we had to clean up VPP constructs. For times when VMs are deleted or migrated, a lot of state was being left behind. I believe that's all been cleaned up now, but when we were starting, that was something we needed to deal with. Tuning the number of huge pages was something we needed to do in order to allow multiple VMs to run. And the huge pages are dedicated per VM. That was important. When we first started, security group support was not there, so everything was open. Not great, but that's fixed now. We had to do a lot of thinking about high availability. So things like process monitoring. Those etcd services that I talked about are monitored by systemd. So even though we've got multiple servers in the cluster, we have process resiliency as well, so that eventually, if something goes down, the controller itself or an etcd process, it'll come back up and join the cluster. We've also got Pacemaker for the VPP agent and the DNS mask process, that DHCP agent I was talking about. The reason for that is that if the DHCP agent moves, we need the VPP agent to follow it. So we use Pacemaker for that logic. Let's see. Oh, and making VPP aware of all etcd nodes in the cluster. This was a big one. Let me go back to the diagram here. So even though there's multiple etcd processes, down on the compute host, VPP only had the ability to talk to one of them, and it did that through the controller IP address, which means that if that controller went away, that particular one, or that process, that etcd process, even though the cluster was still running, you were kind of dead in the water. So we added support down in VPP in the plugin to be able to talk to each of the etcd nodes if there was a problem with one of them. There was a problem with IPv6 subnet support. That's since been fixed, is my understanding. Something that we hit recently was large core dump file size. I believe I heard numbers in like a terabyte. That's huge, a huge file, completely unmanageable. We fixed this through config settings by putting fewer things into the core dump. And also recently we had a VM restart issue, and the fix for that was upgrading to QEMU 2.6. Current limitations. I mentioned that there won't be support for remote group ID support. There won't be support for remote group IDs until release 1707. This is a bit of a bummer for us because of the way that the system acts if there is a remote group ID. when that happens, all security group rules are ignored, and so everything's open. It's kind of bad news, so we're looking forward to having that support. We notice issues with live migration. The VMs get stuck in a migrating state, so we're looking forward to having that fixed. And scalability. I mention this because VPP has never really been run in a huge deployment, and as you know, as things scale up, issues are sure to be found. So finally, I wanted to give you something pretty to look at. Let's talk performance. These are numbers that were published by Red Hat this past February. And what you're looking at here, on the y-axis, you've got throughput measured in millions of packets per second. And on the x-axis, you've got number of flows and increasing complexity. So if you look with 1,000 flows and simple complexity, what I mean by that is the things that were varied in the testing were like source IP address, destination. If you look, the performance is pretty similar between OVS and VPP. And I wanted to mention this is OVS with DPDK. If we were comparing OVS proper, like plain vanilla, no DPDK support, against VPP, the changes, the differences would be much more stark, actually. But let's go with what we have. So at 1,000 flows, the performance is pretty similar. But what's cool about VPP is as the number of flows go up and the complexity increases, so you start changing more variables like MAC addresses, source and destination MAC addresses, and things like that, OVS starts to drop off. But VPP actually remains steady. And the reason for that is because of all of the optimizations that it's making. So as things scale up, we're looking pretty good there, and I think that's pretty cool. So that's actually it for me. If you haven't already, please visit the Cisco booth in the marketplace, meet some cool people, and talk about all the amazing stuff we're doing. And with that, I'm going to hand things off to my partner in crime, Shannon McFarland.
All right, and we'll also have some time at the end. Ann can come back up and you can take all kinds of photos of her answering your incredibly difficult questions. So we look forward to that. That's good. So we moved from a hard thing to a bigger thing. So talking about the entire next generation internet protocol in 15 minutes is always a good time. So we're going to focus a little bit on kind of where things are with IPv6 from a deployment perspective, specifically in the cloud. My name is Shannon McFarland. I work with Ann and many people in the group and work for Lou in the cloud computing area at Cisco. And since roughly 2002, I have ranged from full-time to part-time in the IPv6 world, and you can tell have some affinity to it based upon my Twitter handle of IPv6. So that's the best way to get a hold of me is on Twitter, or just hit me at mcfarland@cisco.com, and we can talk about your IPv4 woes. So from an IPv6 perspective, if you've been under a rock for a period of time, you kind of understand nothing about IPv6 and about this thing called IPv4 address starvation or exhaustion. But if you've been alert at any point in your career, especially in the last 10 to 15 years, you know that we're in trouble on publicly routable IPv4 address space. So based upon the IANA exhaustion, which is the governing body that assigns addressing to RARs, or regional registries such as ARIN, they exhausted their address space a long time ago. Each of the RARs are now in what they call the last call or their last allocation pool. And so these are very, very difficult things to get. So if you are trying to expand your business into an area where you're going to obtain publicly routable space directly from a registry instead of a service provider, you're going to have to do a lot of work to justify that. So for example, today, if you're wanting to go and grab an entire /24 of routable space from an RAR, you better have a really good reason, and it's going to take you a long time to get that space. So, that really is a driver towards IPv6. And there's a bunch of links here based upon the main IPv6 page for each of the RARs that you can get to. Now, what this has done is this has triggered kind of some strange behavior in our market, and it is address market kind of exchange has been created. There is no formal process, if you will, for you to go and acquire IPv4 routable address space from someone else. So what your actual obligation, if you want to obtain someone else's routable space, is that you would go to someone like Aaron, and the selling party or the giving party, in the case of Stanford that gave their address space away, you would go and say, we as Cisco are obtaining this address space that used to be assigned to some other company, and we basically do kind of an agreement around that exchange of information. When that does not happen, we do all kinds of dumb things, right? Because now if you're a service provider, for example, or an enterprise who has obtained v4 spacing or address space from another entity, and you have not done the good work of exchanging that record information from a registry such as Aaron, what happens then is that you can be blamed for bad behavior from an address space that you now own. So blacklisting that exists in various parts of the world, you could be associated with address space behavior that literally you had nothing to do with. And so this creates all kinds of strange stuff in this market. But we see it happening. I mean, just recently MIT sold a bunch of their address space, and Amazon was one of the buyers. We have people that are selling the address space back, and we have people that are actually giving the space back, Stanford being one of those. And the ranging price for this, depending on where you are in the world and how much space that you're actually buying, can range from $5 an address up to upwards of $14, $15 for each v4 routable address. So a tremendous amount of money that's going in to basically stall the inevitable. And this is around IPv6 that is kind of helping us ease this burden. So I go through all of that on the address exchange part simply to point out that you really don't need to do that. IPv6 used to really suck to implement. It has never been hard to get v6 addressing. But it has been very hard to implement IPv6. So we're going to talk a little bit about what some of those strategies look like specifically in the cloud. So real quick, I want to do one slide of what IPv6 is, simply just to do a level set. So IPv6 is 128 bits long versus 32 bits long versus in the IPv4 world. So it's a significant step up in address space. It's hexadecimal based, and this one bullet point is the only reason I ever got into IPv6. Because I'm an IPX guy from way, way back when, and pretty much the only joy I had back then was being able to create inventive names through hexadecimal. Face, bad, cafe, all of these great things that you can do in a hexadecimal addressing space is really what drew me into IPv6, and here I stand. So that part of it is cool. You also inherit a bunch of really cool stuff with IPv6, and this really makes it into a very, very valuable protocol when we're looking at very massive scale type of addressing structures. The ability to discover your neighbors and discover resources on your own segment. The ability for you to have stateless addressing. This is incredibly powerful in the mobile marketplace, where I don't want to carry something heavyweight like DHCP. I just want something to come on the network, discover its own addressing, and be able to get to where it needs to be. And this is really, really good in a first responder environment where you've got to set something up quick. You may not have all the equipment to provide a stateful means to providing addressing. And so the stateless addressing model is very important. Other things that we drop off and gain, again, very much like the VPP versus the OVS story that Ann was talking about, is that we are making optimizations to the protocol as we embrace it. So dropping off broadcast and moving all of the things that we used in broadcast, converting them over to a group-based messaging system such as multicast is a very important asset there. And we can tell, based upon the number of routable addresses on the top versus the bottom, that we've got a fairly significant size increase in our allocation. So when we look at IPv6 from a cloud context, there's a lot of things to consider. I mean, historically, what we've had to deal with from an IPv6 perspective has been focused on upgrading your layer 3 components, right? So routers, switches, getting all the way up to layer 7 from a firewall, and load balancing, and deep packet inspectors, proxies, those types of things have been what we've been focused on. But when you start implementing stuff within the cloud context, there's a lot of dependencies on things that aren't pure routing switching. So those things such as API endpoints, how do you represent through a load balancer your API endpoints? How do you talk to a database? Many things that exist inside the cloud that are very protocol dependent are things that you need to make sure are IPv6 aware. Some of the big ticket items that have nothing to do with the actual direct implementation of the cloud as it relates to APIs and databases are how do you wrap your implementation of the cloud through orchestration. So if you are developing code or you are writing orchestration and automation and you have some sort of protocol dependency there, that's going to be a huge gap because the cloud components themselves may support IPv6, but if your automation that deploys that is not aware that a protocol such as IPv6 exists, it's just a huge gap for you. So what we have kind of led ourselves down the path to is simplifying the IPv6 implementation in the cloud. And that focus has really been on the tenant-facing support side versus the control plane. So we're going to kind of jump over to what some of your options look like as it relates to deploying this in the cloud. So the two common approaches that I talk to customers about is to dual stack everything or conditionally dual stack these components. So let's kind of graphically take a look at this. So on the left-hand side is the dual stack everything approach. This simply is applying V6 everywhere you have IPv4, right? No brainer, of course, right? But when you look from a cloud perspective, that is pretty significant. Because it's not just about, again, L3 through L7 constructs that you need to implement, but it is, okay, well, what happens if I can talk to a database or an API endpoint on two protocols, but something happens midstream to IPv4, right? Someone makes a boneheaded route, change, and V4 blacks out, but V6 is still there. Is it going to work, functionally? Is it going to work the way I expect it to? So there's a lot of research that you have to go through to ensure that these particular things work in all cases. So the one on the left looks like the great approach, but it's going to be a painful one for you unless you really do a good job of kind of testing this out before you implement it. Where the vast majority of customers are going, especially in the enterprise, is what we call the conditional dual stack environment. And this is where they leave their control plane or their service tier alone, their API endpoints, their databases, their automation to get the cloud in place. They're leaving with V4 today, but anything that faces or is consumed by the tenant is going to be a dual stack or an IPv6 only implementation. And this is really what matters, right? Because most of the time the tenant is coming and saying, I want people to consume my application regardless of the protocol they're using. So please enable that functionality. So my tenant-facing environment to include access to the internet is really where we want to focus our implementation, either in a dual stack or in a V6 only type of environment. And so that's really where most of our folks are deploying. Now, when we look at IPv6 from an OpenStack perspective, we've got really strong support. We've had some pretty good support since Kilo, but it has matured. And I'm proud to say, kind of jumping to that last bullet point, that there's people in this room and outside of this room from Cisco that have been really driving the IPv6 support model in each of our releases. And some of those include all of the addressing structures that we have. So we've got SLAC, or stateless address auto configuration. We've got both models of DHCP. And we also have IPv6 prefix delegation, which is super important, especially in the service provider realm. Now, when I kind of parenthetically, say mostly there on the control plane components, it does depend. It depends on which databases you're using and which types of HA models. Are you running Pacemaker or VRRP or HSRP or Keep Alive D, and which versions of those types of things? So when you start to glue your control components together, you really need to do a good job of understanding what the IPv6 support model looks like, and then make a very conscientious decision on, do you dual stack those, or do you go ahead and kill V4 and just do V6? Because dual stack sounds amazing, but again, when you have two abilities to talk to one thing from a path perspective and one of them goes away, you can absolutely see very odd behavior. So some other things that are listed there: security group, LBAS support, and so forth. So wrapping up here, the things that we want to kind of walk away from is IPv6 is here. It's very strong in the OpenStack community, and if you don't have a plan for it, you're late. And so it is never too late to do something about it. But if you're being shocked by the first time with IPv6 in the cloud and here today, then you should be concerned. Because it's going to take you a long time to get this running, and you need to get moving on it pretty quick. IPv6 with your standard L3 and L7 components is not your issue. It is your developmental practices and the tooling around how you implement IPv6 and how your applications work in that realm is really where you need to be focused. Jumping down into here is, again, you need to make a decision around whether you're going to do full control plane support. Are all of your cloud components going to be V6 only, or dual stacked, or none of the above? And from an application development perspective, do you write your applications to be protocol agnostic versus protocol aware? So the idea, that you really want to go through in your application deployment is, I don't care what the protocol is, right? Versus bolt on IPv6 to all of your calls and so forth. And so that's a conscientious decision that you have to go with. The last part here is, don't be paralyzed by the size of the job. Start small, start simple, and start on the tenant-facing side of your cloud, and then just start piecing the components together, and you'll end up with IPv6 before you know it. All of the slides, in my particular case, my deck, there are probably 20 or 30 more slides that you'll want to get, which are all the links to deploying IPv6 inside of OpenStack, and many, many other things. And I think there's some extra slides in there from Ann as well. So you definitely want to get a copy of our decks, which will really kind of take you to that next level of depth that we have. So I'm done with my part. Ann, if we want to take any questions, I think we have a little bit of time.
We have a few minutes for Q&A. If anybody's got a queue, well, I don't even want to have to say it at that point. Yeah, I'm... No.
So we did such a thorough job of two very, very large, complex technologies in 15 minutes that you have no questions. That's amazing. You're a lot better than I thought, Ann. That was very impressive. Oh, no.
I told you, brain cells.
I still got a mic on. I shouldn't say that. Nothing? Gary, we may be able to go to break early. I'm impressed.
The one thing I'll say is that they haven't been all that spot on with the coffee, so you might want to get your line, get the line for the coffee now ahead of the break.
Excellent.
If there are no questions, again, all the slides are up on SlideShare for Shannon and now. The rest of the slides for our other presenters will be up in a couple of days. Thank you all for coming. We've got 2 more sessions after the morning break on NFV and container networking, so come back for those. And on your way out, stage right, you can grab your runs on OpenStack running socks. Yeah, I know, incredibly clever, right? Okay, thank you very much. Thank you all for coming. We'll see you after the break.